I'm just going to go ahead and share my screen. How many days do you guys have for the project in all?
From my side, it's 15 days. Total of 15 days starting from yesterday.
So we are looking at about 2 weeks. Okay. This is the most important thing. Okay. Don't fret. Okay. The project is not an easy project. I won't lie to you. If I tell you it's an easy project, I'll be lying to you. However, it's a doable project. Rome was not built in a day. What you need to do is to break it into pieces and eat it chunk by chunk. Then you can do it. But I'm about to take you through, give you a generic overview of what you're going to expect, some of the things that will be expected of you, some things that you need to be doing when the project is released. Okay, has it been released already, or is it going to be released tomorrow?
Mine was released yesterday on the 7th.
Some of us tomorrow.
Oh, okay, different time zones. That's true. Okay, no problem. So for those of you who have already seen the project, then at least you have a fair idea of what you're looking at, and just the immediate glance at the project can scare you. And that's what I'm trying to prevent. The immediate impression that you may get is that, what is this? What am I looking at? Where am I even supposed to start? I don't even know where to start from. There's too much going on here. And that might be your first impression when you go into the project. But don't do that. That's because the project is a doable project. And the purpose of this meeting today, we're going to meet at least 3 times a week throughout the period of the project, just to try and help you guys as much as possible. Okay. I also have my own personal projects to do, so I can't meet with you guys every day. So the best I can do is that at least 3 times a week, I'm going to dedicate the evenings to you guys, and then we're going to go through it together. But for today, I'm just going to give you a generic overview. For those who have not already seen the project, at least you have a fair idea of what to expect. And for those who have already seen it, the overview is still going to help you to know at least how to put your first foot forward. Okay, so I'm just going to, instead of just going through the instructions and everything, reading, I already know the instructions, so I'm just gonna try and summarize like a few important things for a start. Then when I'm done, I'm just gonna open room for questions. Okay, I think that will be the way we're gonna go today. What you are seeing here is just some advice from Mr. Julian, telling you that don't copy, don't do it, just try and do it on your own. Just some advice from Mr. Julian up there. And then next, you're going to see the resources that they give over here. When you click on these things, they're immediately going to take you to Wikipedia. I think so. To Wikipedia. And I mean, when you hop in here, you might get overwhelmed, like I tell you all the time. So that's definitely not the first thing you want to do. The first thing you want to do is to come to the learning objectives, and then go to ChatGPT and give these objectives to ChatGPT as prompts, so that you get a fair idea of what these things mean. You're not going to get the entire understanding, but you get a very good first idea of what to do about the project. And some of the questions you're going to see in here are: who designed and implemented the original Unix operating system? Just like general knowledge that every developer should have. The most important questions in here are: what is PID and PPID? Is one of the most important questions for this project. And then, how does the shell work is a very important question for this project too. And then, what are the 3 prototypes of main? Very important. How does the shell use the path to find the programs? Very important. And then this function you're seeing over here is also another very important function, execve, very important function. And the next question is how to suspend the execution of a process until one of its children terminates. They're talking about the wait process. In the coming days, these are the things that we'll be dealing with, and we'll find out how to do all these things. And then, as usual, you're going to see the general objectives here. Nothing new, just same old, nothing special over there. Now, the next thing you need to note is that the project is a team project, just like the printf project. So what you have to do is to create one repository. You've already gone through that process, so I'm not going to waste time explaining that to you. Create one repository, then you're going to invite your partner as a collaborator, Your partner is going to clone the repo, then you guys are going to be pushing and pulling. It's a very simple process, and you guys are familiar with it because of printf. So I'm not going to waste a lot of time on that as well. Okay, now the most important thing now is the project itself, and that is what I'm going to take you through in about 30 minutes, and I'm going to leave about 15 minutes for you guys to ask questions so that you know what to do. Okay, when you come into the project, they're going to give you a list of allow functions and system calls, and there are about a good number of them which you're going to be using for the entire scope of the project. Immediately on the first day, most likely you may not understand probably 70% of what these things mean. Don't let it bother you. These are functions that you are going to be using for the project. Some of them are access. Some of the most important ones are the exec VE, as I mentioned to you already up there. You're also going to be needing exit very much. You're also going to be needing fork. For instance, if you want to create a new process. You're also going to be needing which other one is going to be very important? Let's see. Printing an error. All these functions are going to be needful, but some of them you rely on some of them more than the others. But for the start of the project, just have a general fair idea that okay, so there are a group of functions that I'm going to be falling on for this project. As to what they mean, you want to take your time with that because you're going to take it one step at a time. Okay, then as usual, they're going to tell you that they'll compile all your source codes with this warp, Wero, Wextra, Pedantic, etc., etc., and then all your C source code files are going to be compiled, and it's going to be output to the executable file H shell. So meaning that the shell that you're going to create, this is how you're going to execute it: ./H shell. Then your shell is going to be activated, and I'm going to explain all these things to you practically. So if you're a little lost with all these explanations, don't worry. In just about 30 seconds, I'm going to switch to the practicals. I'm going to give you a fair idea of what I'm talking about, right? So then let's say you are done creating your shell, and then your shell is executed, and you're going to have a prompt, and then your shell is going to be activated, and you can use it just like you use your normal shell. Okay, then there goes the task. We're not going to go into the task yet. I'm going to take my time and break a few things down for you, and then we'll now talk about the tasks themselves. Okay, let me take you into my Evernote, and let me talk to you about a few very important things that will serve as foundations for you. Before I proceed, if anyone has a question till this point, you can go ahead and ask before I proceed. Any question? Let's go see who is here. Ayidina, do you have a question? Ayinde, do you have a question? Mr. Edem, Mashilo, do you have a question?
No, I'm okay for now.
Good job. Okay, all right. So we proceed. Okay, now hear me out carefully. The project that you are going to do tomorrow is a shell program. That much you know, okay? Just like you did printf. Printf is a simple function that prints things to the standard output. Here in this case, you are not just creating a function, you are creating a program that can execute other programs. Hear me out carefully, because these will be your foundations. The shell, the program that you are going to create, this project is a shell project. The shell itself is a program, and the program you are going to create will be a program that executes other programs. Before we delve into that, let me take my time and break down some architecture for you, okay? So that you understand what the shell is in the first place, how it works, so that when you know how it works, then you know how to implement it on your own. Just like with printf, you first of all need to know how printf works before you can create your own printf. So with a shell, you need to know how the shell works in the background. Then you can now create your own shell. And that is very important. So before we delve into that, I want you to know that there are four main important criteria of the Unix architecture. What do I mean by the Unix architecture? It's just an operating system. Just like we have the Windows operating system, we have the Linux operating system, we have Ubuntu under Linux. So there are several operating systems. In ALX, we are using a structure under the Unix operating system, and it is known as Ubuntu. Okay, so the shell that you are going to create is going to be a shell of the Unix operating system. You need to get that very clear. Okay, so you are going to create a shell of the Unix operating system. The moment you understand that, then you know that, okay, I can now go and research what is this whole Unix operating system, how does it work, how are files structured in the Unix operating system. You are going to need all these to be able to do your project. But before we come to that, I want to just give you an overview of how the Unix architecture is. Okay, the first part of any Unix system is its hardware. Okay, the hardware is simply the hard part of your computer, your CPU, your RAM, your hard disks, your motherboard, etc., etc. All these are physical components of your system, of your computer. Okay, now this hardware has something known as the operating system. So for instance, I am on a MacBook right now. The MacBook has a certain operating system that causes the computer to work. All right, you may be on a MacBook, or you may be on another system such as a Windows. Okay, there is an operating system within the physical computer that you are holding. Something, the spirit of the computer is the operating system. For instance, this is my body. When I close my eyes and my spirit leaves my body, this body is just a dead body, it's empty. So some life has to be in this body before I can interact with you. In the same way, your computer is a dead computer if there's no operating system in it. There's no life in it. So the life of the computer is the operating system, and that is what causes you to be able to interact with your computer in and out. All right, now in the operating system, I need you to hear me out well, because I'm about to get a bit technical. There is something in your operating system known as a kernel. K-E-R-N-E-L. K-E-R-N-E-L. Kernel. The kernel is a very core component of your operating system. It's like the central component of your operating system. So in this Google class in which we are, assuming there's a class prefect here in this class who tells us what to do, where to sit, which assignments to do, how to conduct ourselves in a classroom, that class prefect is the kernel. Okay, he is the one who determines what everybody does in the classroom. He's the one who determines how to share the books when the assignments are given. And the kernel is what your shell that you are going to create is going to be talking to. Hear me out well, because all these will determine how you are going to write your code. Okay, your kernel, your shell that you are about to create, we'll talk about the shell next. Okay, the shell that you are about to create will be talking to the kernel. All right, and the kernel is going to be handling processes such as file management, process management, blah blah blah. We'll talk about all these later. Don't worry, I don't want you to get overwhelmed as yet. So don't worry about all these things, what the kernel does. We'll break it down later. All right, then now the next critical part of your computer or your system is the shell, and this is what the project is about. Okay, the shell is simply a command line interface that allows users to interact with the operating system and run commands. The shell accepts human readable commands from users and converts it into something which the kernel can understand. I'm going to break it down. Don't worry about the technicality. Let's use some image to understand all we have said so far. Now watch this carefully. This is all I was trying to tell you. In every system, there is the physical components referred to as the hardware. Okay, so this is what we see over here. Then inside the hardware, the first component that we have is known as the kernel, which is next to the hardware. Then next to the kernel, see the kernel as the operating system. Okay, then next to the kernel is what you're about to create, which is the shell. So your shell is going to be talking to the operating system and then receiving commands from operating system, there's going to be a back and forth of your shell and the kernel. All right. Then on top of the kernel are system applications. I'm going to break it down further. All right. But this is a general diagram. Now let's look at a more detailed diagram of how this system is going to work. As part of the kernel is something known as a system call. Okay. As part of the kernel is something known as a system call. These system calls are simply functions that allow you to do certain things. We'll come to do certain things later. This is going to be your focus. The work that ALX has given to you in this project is to create a shell. We'll talk about what the shell is. All right. Your shell is going to be relying on system calls. Your shell is going to be relying on system calls to be able to execute its processes. All right. So I said there is a hardware, there is operating system known as a kernel. Then inside the kernel, there's something known as a system call. Then on top of the system calls is a program known as the shell. This is very simple. Let's go illustrate it and see what we mean. I hope I've not confused you guys as yet or said anything too complicated yet. Are we all on the same page?
Yes.
All right. Awesome. Now listen. This is your computer hardware. So this has your screen, your keyboard, your mouse, and everything. This is our hardware. Okay. And on top of the hardware, we have what? The kernel, which is your operating system, the central component of your operating system. And on top of the kernel, this is what your project is going to be centered on. So this is what we are going to be doing. You are going to build a shell. Okay. Then on top of the shell, you have several applications. There are several applications that are running in your system. So application, several applications. But our focus for this project is going to be this part of our operating of our system, our computer system. Okay. But now the shell has something known as the terminal. Okay. So the shell has something known as the terminal. The terminal is the interface of the shell. What do I mean by that? This is my computer screen. Okay. So this is my laptop. This is my keyboard, blah blah blah, keyboard. This is where I type. Now I open my terminal like the way you open your ALX black box. All right. So let's just go here. Then let me get a sandbox. So I open my web terminal, and then suddenly there is this black box that's going to show up on my screen. Okay, so I've opened my terminal. Great. So I've opened my terminal. Okay, then I type in a command ls. I enter. Then suddenly I receive an output. Okay, this much we know. I do pwd, print working directory. I enter. Then suddenly I get an output. All right. What I'm trying to explain to you is that the ls that you entered over here, that gave you the output. Something went on in the background before you received the list that you are looking for. That thing that went on in the background is what ALX is asking you to build or to create. And that thing is known as the shell. Okay, so this interface, this black interface or whatever color it is that you are seeing on your screen is referred to as the terminal. That is the interface you type in your commands. That is what you see. All right. Get rid of this. Okay. Now, the interface that you interact with is the terminal. But when you put in the command, for instance, a command like ls, what happens is that in the background, the shell picks up this command ls and runs the program. Then the program called the shell understands that, all right, the user is asking me to list out files. All right. So now I'm going to list out files. Then the shell executes the program and gives the output back to the terminal. And the terminal is going to list out the files for you. Or you can enter pwd. You want to print a working directory. Then this command you are putting in the terminal will go to the background and be given to the shell. And the shell will understand that, okay, my user is trying to print the current working directory. So he prints the current working directory, and then the shell will give the output back to the terminal. So like, okay, here you go. The working directory is currently this. So you see, that is the working process between the terminal and the shell. The terminal is the interface you see, and the shell is a program behind the terminal. What is working in the background is what is referred to as the shell, and that is what we are going to be creating. So let me just go into my terminal right now, and then let's understand a few things here. So like I explained to you, this green, it could be any color anyway. This thing you are seeing here is what is referred to as the terminal. Behind this, there's a program that is running. That is why when I type pwd, something comes out. Something went on in the background between this command and this output. A lot has gone on in the background. If I do ls-l, like a long list, before all these things came out, something has gone on in the background between this command and this output. That is what ALX is asking you to create, and it is a very simple process. All right, so let's get out of here and let's go understand more deeper things now that we understand this this workflow. All right, when I'm done, I'll just share this notebook with you guys so that you can take your time and just read through and have a fair idea of what's going on. Okay, then let's talk about the kinds of shell that there are. We're not going to spend a lot of time here, but then it's a very important thing for you to know. So now that we know the difference between the shell and the terminal, you need to understand that there are several kinds of shells. There is a bourne shell represented by SH. There is a bourne again shell, and that is what we are using in ALX. That is bin bash. That is the bash shell. So the bash shell is known as the bourne again shell. So anytime you are going to create a script and you type bin bash, now you are going to understand what that bin bash means. I'm going to show you to you in a minute. There's also another shell called the C shell. There is a K shell. There is a 10X shell, and all these things are in the Unix operating system. All right, keep this in mind. We're gonna come back to it in a minute. I've spoken about the difference between the shell and the terminal now. I want you to see something very important here. All right, because you're going to need it for your program. In every Linux system, there is a way files are arranged in every Linux or Unix operating system, and the arrangement of files in the Unix operating system is hierarchical. It is hierarchical. That is very important to understand. So for every Unix or Linux operating system, there is the root user. The root user is a rubber duck you are seeing over here. Okay, so this is a master user, this is a root user, and every file, both the files of the operating system, the files that you, the user, are creating, or anything that can ever exist on your system, hails or emanates from the root user. Okay, then from the root user there are several directories, and then within those directories there can be other directories. So the question is that where will your shell that you're about to create be in this structure? Where is the shell going to be stored? How are you going to arrange your files? What are you going to do? This is what will determine how you do that. Okay, so like I explained to you, this is the root user. Then from the root user there are several directories which contain configuration files that help your PC to run. Okay, these contain configuration files that help your PC to run, and they are in the directory called root, which is this rubber duck. Okay, now within the root directory there are several directories, but the most important for your shell is the bin directory. The directory is simply a folder. Okay, so the shell that is working on your Linux system is kept in the bin directory. You see why I'm explaining to you in a minute. So the shell that is running, so when I open my terminal, this green thing you see, let me clear my screen. This thing you are seeing here is actually a program. All right, it's not like just an interface. It's a program that is running. It's a file. Let me just put it that way. It's a file. It is a configuration file. It is an executable file. Just like the way you create a script, bin bash, and you write something in it and it does something. This terminal you are seeing here is simply a file. So I can take you into my operating system right now and I can show you that file, and I'm going to do that. and that is what you're going to do for this project. Okay, so I have my bin directory here, bin folder, and I have other folders, but I'm going to take you into this bin folder and you're going to see what is inside it. Okay, so let me first do it in the graphic user interface so that it becomes easier. So let's use this so that at least you have a fair idea of how this whole thing looks like. Okay, all right, so I'm gonna go to the root. Are you guys with me?
Yes, please. Yeah, we are here.
All right, now I'm in my graphic user interface so that we can have like a fair idea of how this thing is looking like in the operating system. In a Linux or Unix operating system, this is the first folder. The very foundation of every folder that exists in the operating system is the root. So that's what you are seeing over there. That's my hard disk drive, right? So in my illustration over here, you're going to see that this is the root user. So that's the first folder. That's your first folder in your system. Okay, and that is what you are seeing over here. So I'm going to open this folder. I'm going to go into it, and I've entered this folder now, and you can see applications, library, system, and users. Why is it that there are only 4 folders in here, but over here I'm telling you that in the root there are so many configuration files over here, but I've opened my root and you're only seeing 4 folders or 4 directories. Where have the rest gone to? Most at times, now hear me carefully, in every Linux or Unix operating system, the configuration files are hidden. They are hidden. They are hidden files, and they are hidden for a very good reason. Now, for instance, I'm going to cd to my root over here. Okay, so let me just cd to root. Great. So if I print a working directory, I'm in root. Okay, so you can see that the root is represented by a /. So the very first folder in your Unix or Linux operating system is the root, and it's represented by a /. Today you're going to understand why you do some things. Okay, so this rubber duck you are seeing over here, this beautiful rubber duck you are seeing over here is this folder. So the / you are seeing is a folder, right? It's a directory. There are things inside this /. It's a folder. That's the rubber duck. Very important. Now I'm going to list for us to see the files that are inside this rubber duck, and you can see that suddenly you are seeing more files than are in the graphic user interface. So everything over here is the same thing here, just that you are seeing more files, and there's a reason why. For instance, look at applications, look at the library, look at what else is here, system and users. So you can see that there is system here, and then there are users here. But then I have many other files when I use the terminal to open this folder. That is because the configuration files here are hidden, and you can use a certain command to let the hidden file show, and it is either Ctrl+Shift dot, or if you're on a Mac, Command+Shift dot. So if I do that, suddenly you're going to see that I have several files that are suddenly showing in this root directory. Are you hearing me? I have several files that are suddenly showing in this root directory, and these directories you are seeing here are what I was calling the configuration files, and they are the ones that you are seeing over here. As part of these configuration files is a folder known as the bin. The bin is just a short form for binary. It is a short form for binary, and the reason why it is referred to as a binary directory is because it contains executable files that only the computer understands. It contains executable files that only remember that the computer speaks binary language. So whenever you are writing your shell script and you do bin bash, the bin over there is a short form for binary. Today you have understood that. Okay, so what we are going to do is that I'm going to go into this bin, all right, this binary directory, and let's see what is inside it. So I'm going to clear my screen. Okay, I'm going to cd into the bin, and then I enter. So I've entered the bin now. I'm going to clear my screen. You can see that I'm inside the bin directory, and let me ls and let's see what's inside it. So I'm just going to ls. We can see that there are very interesting files here. Okay, but I want you to take note of some there are several files. All of them are not of our concern, but you see something. Look at this. Are you familiar with this command? Are you familiar with make ls? Are you familiar with pwd?
Yeah.
Are you familiar with rm? Are you familiar with remove directory? These are things you've been doing. Okay, you may not be familiar with all of them, but these are shell commands. Okay, these are shell commands, and you ask yourself that, okay, so are these things in the bin of the graphic user interface too? So this is a bin folder. You realize that the hidden files are faint. Anytime you are in a Unix system and you see faint directories or faint folders, it means they are hidden files. The last thing you want to do is to mess up with the files inside them. So when you enter these, when I'm done, I'm going to take you into the ALX sandbox, and you're going to realize that all these files are actually inside it. Okay, so when you go into the configuration files, you shouldn't mess up with these files, because these are the files of your operating system, just like I was explaining to you. So in our diagram over here, we are currently here. Okay, we are currently here. We are inside the system calls. That is where we are. So all these directories that you are seeing here are system files that help your computer to run. If you mess up with them, your computer can shut down. Okay, so I'm going to go into it. I'm not going to mess up with these files. However, I just want you to see how they look like. So if you look at it carefully, I'm going to maximize it a bit. You're just going to see black, nothing special. But you can see that all of them are executable files. Okay, that's why you are seeing exec. So all these things you are seeing are executable files, and they are programs that are inside my computer's operating system. And all these things you are seeing here is what you are going to be doing for the Simple Shell project. You're going to be creating many of these things. Not all of them though, but the most important thing we are going to look at here is the bash program. I'm going to go back to my Evernote, and I'm going to let you see this. So I told you that there are several kinds of shells. There's a bash shell, right? Bash. There is a C shell, there is a K shell, there is a T shell, and several other kinds of shell. One of the most recent shells is also the Z shell. So here in my graphic user interface, you can see that this is the bash program. This program you are seeing here is what is referred to as the bash shell. Okay, then you can see other shells in here. Let's see, you see the T shell over here. This is a T shell. And then let's see if we can find the K shell. Where is the K shell? Where's the K shell? K. This is the K shell. You see? So all these are programs. Okay. Let's see if I can find the C shell. So where's C? This is the C shell. You see? All right. That's enough black boxes for today. So I'm just gonna exit out of the bin in the graphic user interface. I'm gonna go into the bin in the terminal, as you see. So these are the folders inside the bin directory. Now what I'm going to do is that I'm going to try and open any of these files, and you are going to see what happens. So I'm going to open, let me start with bash. Okay, I'm going to open this bash directory or file that you see. You know what, before I open it, let me just clear my screen. Let me clear my screen and list in the long format, ls-l. Okay, now it's too much, so let me just minimize it a bit. So that you see what I'm trying to do. Okay, so you see that this is the bash file. They are all files. That's why they're starting with dash. If you remember shell permissions, anything starting with a dash is a file. Okay, and then there are several other shells here. There's a K shell, there is a Z shell. All right, now I'm going to open. Let me bring this up a bit. Just bring this up. I hope you can see down here. Can you see down here? Can you see the parts I'm highlighting?
Yeah,
the red part. You can see. Great.
Yeah.
Great. So I'm going to open bash. Okay. And then see what happens. Now I've entered. Do you see what just happened? Another process has been initiated. Another bash session has been initiated. Listen to this very carefully. Let me close this. Okay, I'm going to terminate the process, and I'm going to open, let me try and open another kind of shell. Let me try, let's say, the Z shell. Okay, so I'm going to open the Z shell, and I'll enter. Do you see what just happened? Look up here. It says that Z shell. Right? Then you can see that even the command prompt has changed. Now it's a percent sign, and it's the same shell that actually you've been working. If I ls, it will list out files. If I clear my screen, it will clear. If I print a working directory, it will print. If I echo, let's say I echo my name Leo, it will do it. You see, the shell works the same way as the shell you have been using. It's the same shell. Let me try it to one last shell. Now, let's say I try to open. Let me try it with a K shell. Let's see how the K shell looks like. So I'm going to open the K shell, and then look at what happens. Another instance of a shell has been opened, which is the K shell. These are programs. They are executable files. So all this terminal that you have been doing, the ALX thing, the black box you open and you are typing your git add, git push, git commit, inside it, you are actually interacting with a program. You are interacting with a file. But this interface, okay, this interface you are seeing is simply the terminal. It's like your screen. It's like the terminal that allows you to enter the computer and interact with the shell program or the shell file in your operating system. Okay, it's a very foundational understanding that you need to be able to move forward. Now, there's one more thing I want you to see. You realize that whenever I open a new instance of the shell, the first thing that you're going to see is that it gives me the login date and time. So up here, it says that last login is Tuesday, August 8th at 7:45, because that's the time over here on this thing. We'll explain, understand what this thing means later. Then it tells you that bin. Do you realize that now it's no more K, it's no more bash? What you are used to is the bin bash. But this time around, it says that this K shell is in a bin, it's in a binary folder, all right, but it is a K shell, not a bash shell. All right, and that is very critical. All right, so I'm just going to close this instance. Is it raining? It's raining. Amazing. It's raining over here. Okay, so let's move on. Now I'm going to clear this. Okay, I'm going to clear my screen, and I'm going to take you into another. All these that I'm explaining to you, just don't worry, just enjoy it. Today I'm giving you a general overview. These are cardinal things that you'll be needing as the days proceed, but just enjoy it as a general knowledge. Then we are going to go into the practical aspect of code much later. We're not going to do that today. All right, I'm going to go into something which is working in the background of my PC, and I'm going to show you something. So if you're on a Windows PC, there is something known as the Task Manager. Are you guys familiar with the Task Manager?
Yeah.
Awesome. Great. So you go into the Task Manager, and what do you see there? You see a lot of programs running. Okay, it's unfortunate I'm not on a Windows PC. I would have shown you what I mean. But I'm on a Mac right now, and there is something like a Task Manager on a MacBook as well. And it's a similar thing on almost every PC. So I've opened my Task Manager right now, and you're going to realize that there are programs that are running currently on my PC. So things are going on in the background. I have so many processes that are going on. Hundreds of processes are going on right now as my PC is on. Okay, you can see that I even have my music open, and I've not closed that portal, so it's there running. And as I'm scrolling up, you see this is the program that I'm using to record the screen. Okay, my Chrome is open. That's where ALX is. I have my Windows server open, but there's something that I need you to see. That's why I brought you here. You're going to see something here called the kernel task. It's part of the processes that are going on in my operating system. Okay, why did I bring you here? I brought you here because you need to understand that for every process that is running on your computer, it has a unique ID number. Every single process, as long as it's a process on your PC, it is being tracked. and it has an ID number. Even if you go on Google Chrome and you open the incognito tab because you don't want it to record your browser history, because you are going to certain sites that you don't want anyone to see later, okay? Even if you go on this incognito tab and you are done and you close it, the process ID is recorded in your operating system. As long as something went through your computer, it is recorded. And this is where it is being tracked at. Now, if you look at this part carefully, you're going to see something here called PID. Okay. I just click on it and it went away. Let me just pull it out a bit. So I'm pulling it out. Do you see this? The fonts are very small. I can't increase it, but I hope you see it. Do you see this?
Yeah, I see.
Great. So there is something called the PID, and the full meaning of the PID is known as the process ID. So every process that is going on in my system right now has an ID number. Very critical. Then you can also see something here called threads. Now, what does that mean? So let me take one program, for example. For instance, let me take anything. So I'll take anything, like, let's say one of the kernel tasks. You can see that the threads are 171, but then the PID is 0. Okay, I'll explain what that means to you. And all this you're going to do with your shell project, by the way. So I want a process which is very familiar so that I can explain for you to understand. Let's use this, my Creative Cloud application. So I use my Creative Cloud application to do Photoshop, InDesign, and all that. You can see that the process ID for this Creative Cloud app that's running on my PC is 496, and it has 23 threads. What does that mean? This means that the application that I'm running on my PC, there are 25 sub processes that are running under that one application. Now it's 23 because it keeps changing. All right, it's very dynamic. Okay. Now, if I come into my PC, my terminal, now I'm going to increase the font a bit, and I type the command top, and enter. Immediately, it's going to give me all the processes that are running in my computer. And this is not just applicative for my terminal. This is the ALX sandbox now. So let me clear the screen. Okay. I'm going to type the command top. Okay, and then when I enter, you're going to see that these are the processes that I'm running in the ALX sandbox right now. So the root, this is the PID I spoke to you about, the process ID. The root has a process ID of 1. That is very critical. You're going to need that later. And then I also have some other PIDs here. Then there's a memory, the CPU usage, which is currently 0. All that is, the processes that are running here. But if you look at my computer right now, I have the process ID of all the programs that I'm running, and then I have the CPU memory that it is taking, and there are other details here that you don't have to worry about. Now, the reason why I'm showing you this is that for every program that's running on your computer, it has a process ID that is being tracked. How is it being tracked? It is being tracked within the shell. It is being tracked within the shell and the kernel of the operating system. This is important. All right, so let's go and write some C code. Let me just go to my VS Code. Where is it? I wrote some code earlier on. So you see that my music folder is open. That is why you are seeing that. So let me just bring VS Code here. Okay, now this much, you guys are familiar with this program. So this is a C program, include standard input output.h. We'll talk about this in a moment. Int main, you already know what this means. And over here, you can see that I've declared a variable. Int number, it's an integer data type, and I've given it the value 17. Doesn't mean anything. But there's something important. I'm going to talk to you about this in a minute. So let's skip that. I'm also going to talk to you about this in a minute. So let's skip that. This is printf. You are very familiar with printf. So I'm printing with the format specifier %d, and I'm printing the number, this variable. I'm printing it here. Okay. Then another printf which is printing something else, which we are going to talk about. Now I've explained to you that every process that's running in your computer has a process ID. So let's try and see how it works practically in code. All right, so if you look at this PID_T, is a data type. It is a data type that is used to track process IDs in every operating system. Okay, so for instance, when I was declaring this integer variable, the data type that I used is int. These ones you know. But here in this case, I'm using another kind of data type which you may not know of yet. It is known as PID_T, and it is used to track the process IDs of the processes that are going on in your operating system. All right, let me go read something to you in my notebook about that.
Leo, sorry to disturb you. Can I please ask before you move?
Yes, go ahead. My PC is slow, so it's the best time.
What's the difference between file descriptor and the process ID?
Okay, I think that's kind of advanced for what we've got into. But then you see that in, for instance, do you remember the write function? You use the digit1 for the file descriptor of the standard output. Do you remember that?
Yeah, I still remember that.
Very good. So in the underlying low-level programs, there are file descriptors, and each of them have special ID numbers. When you are running any process on your PC, they receive random process IDs. So I'm going to show you right now. That's what I was trying to show you. They are going to get random process IDs, but certain file descriptors have numbers that cannot be changed. I hope you get that. So for instance, there is a function called the init process ID, INIT, and that is like the foundation of all processes, and it has a process ID of 1 that cannot change in the operating system. So anytime you're talking about the foundation of all processes in your operating system and you refer to the init function, you know that it definitely has a process ID of 1. But then other processes may be given random process IDs, and it's not a problem. So whenever you are talking about file descriptors, you know that you are dealing with special files that have certain designated process IDs. I hope that makes sense. It might sound confusing to some others, but we'll come to that. Probably not today, but very soon. But does that make sense to you?
Yeah, a bit. Init, you say the init function falls under the system calls or library calls.
Come again.
You say you spoke of init functions. I'm saying init function falls under the system calls functions or the library calls functions. So I can look into it and
it falls. Yes, it falls under the system calls function.
Okay, so.
Yeah. I don't know why my notebook is actually unable to. Let me just get rid of this.
Hi,
yeah, hello.
Okay, sorry please. My name is Beckham, and I want to ask, are you recording this?
Yes, I'm recording the session. When I'm done, I'll make it available for you guys.
Okay. I don't want to ask questions that will bring you back.
Got it. I'll do that. I don't know what's happening to my Evernote, but it's not working. But let me go ahead. I was trying to show you the process IDs. Sorry about that. Okay, so now I'm going to run this code. This you're seeing over here is a data type, and this is a variable. So I could have named this anything. This process ID you are seeing here, I could have called it anything. So I'm using the data type PID_T to try and use this variable to hold the process ID here. Okay, then I'm using this function called get process ID. We're going to talk about this function in our subsequent sections. There's a function known as get process ID, which can use to get the process ID of the current process that you're running, right? Then the next thing you need to understand is that those functions are inside the Unix standard header file. I remember I've spoken to you guys about this before. Okay, so the Unix standard header file is a very cardinal function you're going to need in this project that holds a lot of the system call functions you are going to be needing for this project. The Unix, so many of the functions that I was showing you in the intranet, a lot of them are the Unix standard header file functions. A lot of them, like 50% of them, are Unix standard. And this get PID function is a part of the functions of the Unix standard header file. It's a low level function. It allows you to interact with the kernel, right? Kernel system calls. You remember the image that I showed to you? My Evernote is misbehaving, so I'm unable to exit from the interface. But the other files are very important files I need to show to you. So this system calls you see over here, the Unix standard.h header file allows you to use functions in here. Okay, so when you are creating this shell, you are going to be calling a lot of the functions in this system calls. That is why I had to show you this diagram, right? So we are going to be creating a shell. You'll be calling a lot of system functions, system call functions. That is very cardinal. So that is this function that you are seeing over here. It gets the PID. Then I'm printing the process ID of this process. So I'm going to run this code and let's see what we get. I'm getting some errors here, so let's see what the error is. Gets PID. Right, let me just get rid of this. So I'm getting the PID here. Process ID. I'm getting the PID. %u is the right format specifier because it's an unsigned data type. Process ID. I don't know why I'm getting an error, so let me run it again. Great, I knew there was no error. Right, so you can see that this is the number which I'm printing. Let me just clear my terminal so that it looks clean. I'm gonna run this code again. So I'm printing the number 17 with this printf function. So printf number, right? I'm printing this number and that is 17. And I'm saying with the next printf that the parent process ID is %u. And I'm printing the process ID, and you can see that this is actually not the parent process ID, it's just the process ID. We'll understand these later. So the process ID is this number you are seeing over here. Okay, so these numbers that you saw in my operating system, these numbers you are seeing over here, for this session that I'm running in my little C program that I've written over here, this is a process ID 66984, and each session has a different process ID. So you realize that when I run this process again, now I'm running the program again another time, and the value that I'm going to get is different. Initially it was 66984, now it is 67 something else. Now let me run it again. If I run it again, I'm going to get another value. Now it is 67060. I can keep running it over and over and over. I'm going to keep getting different values. Now it is 670. So the reason why I keep getting different values for the process ID is that in your shell, every single process has a different process ID. This is very foundational, and you need to understand that every single process has a different process ID. However, each process has a parent process ID. I think today we can't jam a lot of things up. Let's move all these technicalities to tomorrow, but at least let's have a general overview. Each process has a parent process ID. So there is the parent and then there is the child. There is a parent and then there is a child. The parent gives birth to the child. The child holds the parent ID of the parent. So each child has a parent. The parent ID of the parent is different from the ID of the child. That is very critical. So all these different processes that I'm running are the ID numbers of the child, and they are different sessions. But if I decide to print the parent ID of this particular process that I'm running, it's going to remain the same because the parent is the same. The parent doesn't change, but then the sessions are different. I'll explain all these later if it's confusing to you. So the function to get the parent ID is PPID. So get parent process ID. Then I'm gonna probably say that I'll change the variables and I'll call this parent process ID. Then let's call this parent process ID. Let's call this parent process ID. Then we're gonna say that the parent process ID is this. So let's run this code and let's see what we get. So you can see that the parent process ID of this process is 66925. I'm gonna run it again. You can see that I'm getting the same number, 66925. I'm gonna run it again. I'm gonna keep getting the same number because it's a parent process ID 66925. Because this time around, I'm not just getting a process ID of the particular session that I'm running. I'm getting the process ID of the parent session. What do I mean by that? Now I'm taking you back into my my terminal. Now we're gonna realize that the processes are still running. This shell session that I've opened is a parent process. So every program that I'm running currently in this shell session is a child of the parent process of the shell. It's like I feel like I put it too much together. Dear God, I'm coming. Let's just go to the sketchboard end. So I open a shell session. Okay, I open a shell session. This shell session that I've opened has a process ID, whatever number it is. Let's say 7986. Then I'm gonna run several processes in this shell. If I run this process has a process ID of, let's say 1. No, it can't be 1 because let's say 32. All right. Then I run another process. It has a process ID of, let's say 690. Another process has a process ID of 693. All these are child processes of this parent ID. Okay, so the shell session that I'm running currently is this process. It has the process ID of this number, and then this parent process has children processes that are running. So this is a child process, child process, child process, and all these child processes have one parent ID. So the reason why when I was running the code in here, the parent ID kept remaining the same is that each session is referencing the same parent ID, and then the child processes, the individual sessions that I was running with the get PID was giving me different process IDs. Okay, so let me give you takeaways for today. Today is just an overview. Let me give you takeaways. All what I've been trying to tell you from the beginning till now, take this home, that for now all you need to understand is that every process that runs in your computer has a process ID. That is what you should understand now. Now let me take you into the internet, and then I'm going to show you a few things that tomorrow you should do. So now here I am in a simple shell project. When it is released, you're going to see this thing, everything you need to know to start coding your own shell. When you click on that, it's going to bring you here, everything you need to know to start coding your own shell. And the first thing that you're going to need to understand is the process ID and the parent process ID. Okay, that is why I was trying to let you see the practicalities of the whole thing. You know, right at this stage, you already know what the process ID is. You know that every program running has its own unique ID number, and it is known as the process ID. And then every process has a parent process ID. The parent process ID is the PP ID. Very simple, straight to the point. And then you know how to use the function get PID and get PPID to get the process IDs and then the parent process IDs. So that is the first requirement of the simple shell project. That's what you should know. Then the next thing you should know is that you need to understand arguments in the shell environment. We're going to talk about that tomorrow. And the next thing you need to know is how to execute a program with this function, execve. That is one of the functions I was referring to. We're going to talk about that tomorrow, and that is very simple too. Then you also need to know how to create processes with the fork function. So let's say you have a process going on here. I have this parent process going on here. I can create a child process over here. Okay, so this is a parent process, this is a child. For me to create a child process of the parent process, I use the function fork. Okay, and that is very simple. Then you also need to know how to use the wait function so that you don't create zombies in your system. You understand what zombies mean tomorrow, and then you can combine the fork and the wait functions and the exec functions so that you don't create zombies in your system. That is also very simple. We'll talk about that tomorrow. You also need to know about file information. You also need to know about environment variables. We'll talk about that later. You also need about the parameters of the main function. Hitherto, what you have known about the main function we are declaring a C program is that you do int main, and then this thing is always void. Then you write your code here and you return 0. You return 0. But in this project, you are going to be introduced to parameters of the main function. You're going to realize that this int main that you have been writing all the time can actually take parameters, and that's what you're going to be seeing here. So apart from the int main void, now the int main can take arguments, int AC and car. We're going to talk about that later too. It's very important for you to understand the project, and there's some exercises here. So now these are the takeaways from today's session. Every process has a process ID running on your system, and that process ID has a parent process ID. And the grandfather, the arch grandfather of all process IDs is known as init. That's what I was trying to explain to my brother. So init, the init has a process ID of 1. So it always has a process ID of 1. That is the grandfather of all process IDs. And then all the processes running on your system is under the init process. So let's say if this parent process ID was running and then suddenly it was terminated, and yet there are all these children of this process ID that has been left hanging in your system. Their parent is dead, so they are orphaned. So what's going to happen? Someone has to take care of them. So immediately this init grandfather is going to take care of these orphans. So suddenly the parent process IDs of these children is going to change from this one to 1. And you're going to understand what such things also mean from tomorrow and onwards. Okay, I think I've spoken a lot, so I'm just going to open the floor for questions, just in case I just carried all of you and threw you into the river.
For a bit of clarification,
Yeah.
PID
Yes.
are subsets of PPID,
Perfect. Yes.
and PPID. So more or less, if it's a set, then the universal one is the init.
Universal init. Perfect. Very good.
And then in the init, there is a PPID. They said that in the init there could be a lot of PPID.
There could be infinite PPIDs. So, for instance, infinite child processes. You see that these are child processes, okay? These processes can also give birth, so they'll have grandchildren. These grandchildren can also give birth, so they'll have great-grandchildren. And each of these also have their process IDs. So the children can give birth to children. Children can give birth to children. And the reason why all these will start making sense to you when we start doing hard-on coding of the shell itself. Now you're going to realize that you'll be dealing with a lot of code that you'll be seeing PPID. What is PPID? You'll be seeing PID. You'll be seeing fork. You'll be seeing exec VE. You'll be seeing init. So all these practical things is what will now make these things make sense to you. That, oh, okay, so this init. So the moment I see init, now my mind knows that, okay, perhaps the parent of this process is dead, and then the grandfather has taken charge. All right. The moment I see something like fork, then I know that, okay, some child process has been created. The moment I see something like wait, then I know that something has been put on hold. All right. So all these things you're seeing today may seem abstract and obscure, but don't worry, it's just the first overview. So I don't expect everything to make sense to you. I was trying to show you guys a lot of things in the notes, but my Evernote is just misbehaving. I don't know exactly why it's happening that way, but this is not even the notes that I prepared for you guys today.
Then one more.
Yep.
There's one instance where there could be PID without
Yes, there could be so. It could happen that way.
There could be an instance, right?
Yes, there could be. There could be.
Can you explain that bit better? How is it possible to have PID without having PPID? Isn't that PPID needs to give birth to PID? I'm not sure if I've got that correct.
Please come with your question again.
I'm saying, is it possible to have PID without PPID?
Yes, it's possible. Very possible. It's absolutely possible. As we proceed, where's my notebook? As we proceed, you are going to understand something called an orphan. I think somebody got to mute their feed. You're going to understand something called an orphan. All right. There's echo in the system.
And that is solo.
Yes, great. I'm really trying to get my Evernote open because all the questions that you guys are asking is inside that file.
I was like, whenever I have a problem, like how you're having a problem with Evernote, I just kind of, how do I show the process of that particular program.
Okay.
And then I just open it again. I don't know if you can check the program. I was thinking maybe that would be helpful.
Okay, so are you asking of that question in relation to the Shell project or in the computing in general?
In solution to your problem and also how it affects our program. Whenever I show the process, like let's say whenever I go and I start the process ID of the program that is run or start, and then I just kill it. Then I reopen it again.
Perfect. So with that, what happens is that you have killed a certain parent process. If it has child processes running, then what's going to happen is that those child processes are going to become orphaned. And depending on how your code is structured, they may end up as what's the word? They may end up as zombies. There's a term in shell scripting known as zombies. So if you kill the parent and then the children are orphaned, you may end up with zombies. Or sometimes the children are dead and then the parent will be left alone. And they have consequences that occur in the program. But we're going to see the practicalities of that later. I think my program is working now. So what I was trying to show you is process management. I actually have a series on YouTube, Unix shell scripting. It's a very cardinal foundation for some of the things that we'll be doing in this. Great. So we can't do this today because we're already out of time. I have to hop into my session. But then tomorrow we'll probably talk about processes, the state of a process. You can see that there are processes that will be running, ready, blocked, terminated, etc. There's a zombie process, suspended, swapped. All these are going to reflect in your code. Okay, and then there's what is known as the process control block. And there's context switching, there's process creation, and you do that with the fork function. These are the things that I was trying to show you earlier on, but we'll talk about that tomorrow. And then how to create a process, how to use the wait functions, the execve, a few of them, yeah, the execve and some others that we'll talk about later on. So for now, in answer to the question that you asked, yes. Remember that the grandfather of all processes is the init process, all right? So beneath that, there are several hundreds of processes that could be running. And then beneath those processes, there are several child processes that could be running. A parent can die and leave the child alone, or a child can die and leave the parent alone. And all these have consequences. And we are going to be seeing them later on as we progress, right? But go into the concepts page, and I'm going to drop some resources for you guys on the WhatsApp page so that you guys can start watching some videos and start reading some articles, so you start gathering understanding. And then read about arguments. At least you have a certain idea of the PID, PPID today. Then read about how to execute a program, because these are the things that we're going to be needing for tomorrow, and then how to create a process with the fork function, etc. So that's that's where I'll end it for today. If you guys have questions, I'm still taking questions. Then we'll pick it up from tomorrow.
They are not in the WhatsApp chat.